So now we're going to talk about subsequences. So subsequences have a pretty intuitive definition, or at least the idea is pretty intuitive. You know, if I have a sequence, I can make a new one just by picking out some of the terms of that sequence. So we'll make that precise. And then we want to prove these three kind of happy theorems. So the first one says that if a sequence converges, then all of its subsequences converge to the same limit. So as a kind of converse, or you can think about the contrapositive of this. You can think that if you have a sequence where you have two subsequences that converge to different limits, then the sequence can't converge. And we've actually kind of already seen this in a few examples we'll discuss. Then we'll prove that every sequence has a monotone subsequence. And then because we know that bounded monotone sequences converge, we'll be able to prove that every bounded sequence has a convergent subsequence. And this is a nice theorem. This is called the Bolzano-Weierstrass theorem. Okay, so first you need to talk about subsequences. So, you know, if I have a sequence, if AN is a sequence, then a subsequence, let's call it, you know, A and K, such that K is an N, is a sequence obtained by picking, you know, a term, you know, in 0 that's less than n1, less than n2, etc. So that's what these NKs means. So I just pick these, you know, an infinite sequence of natural numbers that's increasing, and then taking the terms an0, an1, an2, etc. from my original sequence. So this is sort of the intuitive idea, and it's not a very complicated idea. It's a little bit complicated to make precise because for our definition of a sequence is, you know, a function with domain and natural numbers. So then I have to see, you know, how can I think about one function with domain and natural numbers being a subsequence of another function with domain and natural numbers? But it's not so hard. But this is how you should think about it. You should think about, you have your elements of your original sequence, A0, A1, A2, etc. And then I just pick some of them. I say, okay, maybe I want to start with A3, and then I'll pick, you know, A5, and then I'll pick A17, and so on. So for example, you know, the sequence 0, 2, 4, 6, 8, even numbers, is a subsequence of the natural numbers. You know, 0, 1, 2, 3, 4, etc. Because, you know, I said, okay, so start with the 0th term, but then instead of the first term, pick the second term. So that one goes there. And then for my second term up here, pick the 4th term down here. Okay, so let's just give a definition to make this precise, but don't worry at the definition if it's a little confusing. So remember that a sequence is a function with domain and natural. So we'll say that B from N to the reals is a subsequence of A from the naturals to the reals if there is an order preserving one-to-one function, let's call it F, going from N to N, so that B, the function B, is just A composed with F. So first I do this function F, and then I do this A. So we have this little map, this little diagram where I have the naturals, and then I have the reals, and I have this sequence A, and then I have this other sequence B to the reals, and then there's this way of including the naturals in themselves with this function f, where I preserve the order. So if I want to get this function b, I just go this way instead. I just first do f, and then I do a. So going that way is the same as going that way. But again, this definition, I think, makes it seem more confusing than it is. You just pick some of the terms. Okay, so so subsequences are sequences, so they can have limits just like sequences. And first, we'll prove the first thing I mentioned, which says that if you have a convergent sequence, then every subsequence converges to the same limit. And also that if a sequence diverges to infinity, so does every subsequence. And if the sequence diverges to minus infinity, then so does every subsequence. So here's our first theorem. Theorem says that if an converges with limit, let's call it a, then any subsequence also converges to a. If an diverges to infinity, any subsequence also diverges to infinity. And if the sequence diverges to minus infinity, any subsequence also diverges to minus infinity. Okay, and one thing that we'll use a few places in this theorem is that if so we'll use that this n sub k, or this way, this n sub k is always greater than or equal to k. So the n sub k, so a n sub k is the kth term of the subsequence that's defined by the kth term is the n sub k term of the original sequence. And the point that since the function is increasing, I'm just picking out some of the elements of my original sequence in order. The index of like the first term of my subsequence has to be bigger than 1, right? Okay. Good. So this is not very hard to prove by induction, but we won't do that. But maybe I'll say you could prove as an exercise if you want to. Okay, so let's prove this theorem. All right, so let's suppose that I have a subsequence a sub nk, where k is an n. Okay, and then let's consider some positive epsilon. Okay, so there exists some natural n, so that if n is bigger than or equal to n, a sub n minus a is less than epsilon. So since a sub k is bigger than or equal to k, we see that if k is bigger than or equal to n, then n sub k is bigger than or equal to n sub capital N is bigger than or equal to n. So we have that a n sub k minus a is less than epsilon, since n sub k is bigger than n. So by this fact here, we have that less than epsilon. Okay, so this says that, I guess in the beginning of my assumption, I'm in this case where we're assuming I'm proving this thing here. So if it converges with limit a, then any subsequence also converges to. Okay. So if the limit as n goes to infinity of an is a, limit as k goes to infinity of a n sub k equals a as well. Okay, so these cases are even easier. So let's just think about the first one. If the limit as n goes to infinity of a sub n is equal to infinity, then for any x and r, there exists some capital N, so that if n is bigger than or equal to n, a sub n is bigger than x. So for k greater than n, we have that again, n sub k is greater than n sub n is greater than or equal to n. So we have that a sub n sub k is greater than x. And this tells us that the limit as k goes to infinity of a sub n sub k is equal to infinity. And I'll just say that the proof for minus infinity is similar. Oh, okay. And so one thing that we could say now, so here's another example. We can now give a really quick proof that the sequence minus 1 to the n doesn't converge, which remember we just proved this kind of from the definitions when we talked about sequences converging, but this doesn't converge since the constant sequences 1 and minus 1 are subsequences with different limits. So if it did converge, each subsequence converges to the same limit. Okay, but this doesn't converge because I have two subsequences that converge to different limits. Okay, so that's just kind of a nice thing, and it's a way of proving that some sequences don't converge. And now, okay, so now we shift gears slightly to think about monotone subsequences. So here's the next big thing we'll prove. Let's list this as a lemma. So our lemma is that every sequence has a monotone subsequence. And the proof of this is very, I mean, it's not very hard at all. And maybe you should, pause the video and think for a second how you might try to prove this. Basically, what you can show is that if you can't make a infinite decreasing sequence, then you can make an infinite increasing sequence. Okay. So so here's the proof. So let's call well, okay, so let's suppose that we have the sequence a sub n. Okay, and then let's call a term a sub n dominant. If for all m that are bigger than n, a sub n is bigger than or equal to a sub n. So dominant terms are bigger than all the terms after them. Okay, so if a sequence has infinitely many dominant terms, then the subsequence just consisting of those dominant terms is a decreasing sequence. Okay, so then we think, what happens if a sequence doesn't have infinitely many dominant terms? Well, what does that say? That says that if I go, let's say I go after the, so say I have finally dominant terms, so say I go out far enough the sequence to not have any more dominant terms, and if I pick any number or any term in the sequence, there's some strictly bigger term later in the sequence. Because if there wasn't, then it would be dominant, but I went past all the dominant things. So then I just keep doing this, and that gives me an increasing sequence. So let's just write that down. So if the sequence has finitely many dominant terms, let's call them a sub n0, a sub n1, down all the way up to a sub, I don't know, nk. Then if m is bigger than n sub k, there exists some, let's call it n now, n bigger than m, such that a sub n is bigger than a sub n. So if this didn't happen, then that would say that a sub m was dominant, but a sub m can't be dominant because these are all my dominant terms. There's only finitely many of them. Okay, but now we can just inductively construct a dominant sequence, an increasing sequence. So now we can inductively construct a dominant sequence, an increasing sequence. I keep saying dominant when I meant to say increasing sequence. So the 0th term can be this a sub nk plus 1. So just the next term after the last dominant term. And then if j terms, let's say a and 0 all the way up to a sub nj have been constructed, so this a sub n0 is that a sub nk plus 1, have been constructed. We can pick the j plus first term by choosing some nj plus 1 that's strictly bigger than nj, such that a sub nj plus 1 is bigger than a sub nj. And I know that I can do this because this a sub nj term is not dominant. So there is some bigger term after this. So possibly this is slightly confusing sounding, but just to kind of summarize the proof again, either I just take these dominant terms. So if I have a term that's bigger everything after that, if I just pick all those terms, that just gives me a decreasing sequence. And then if I don't have those things, that means if I go out far enough, then given any term, there's always a bigger one after it. So then I can just inductively construct a sequence just by keep adding on another term. Okay, so now we can prove this really nice theorem. That's the Bolzano-Weierstrass theorem. So let's mention the proof of this here. So this is Bolzano-Weierstrass. I think this is our first named theorem of the class. And this theorem says that every bounded sequence has a convergent subsequence. Okay, so how's the proof go? So given a bounded sequence, by the lemma, it has a monotone subsequence, and it's still bounded. And it converges because we prove that bounded monotone sequences converge. Okay, so the real work in this theorem went into proving, one, that bounded monotone sequences converge. And remember, this was not completely straightforward, right? Because it used completeness for the reals. And then also this theorem we just proved, which I guess is pretty straightforward, which says that every sequence has a monotone subsequence. All right, so now that we've done all this, we're basically set up to prove that a sequence is convergent if and only if it is Cauchy.